Great, thanks, Gerbs. So I'm here to talk about the Near Earth Object Camera, or NEOCAM project. And I'd like to acknowledge the team, many of whom are here. We've got a bunch of people who are giving posters. We've got some of our contractors from the Space Dynamics Lab who are here, some folks from Ball Aerospace who are also part of the project. So anyway, it's a pleasure to work with all of them. So let me talk a little bit here. So our top goal actually comes from really the top. As the administrator mentioned, we now have a national near-Earth object preparedness strategy and plan. And its top goal is this, number one here down at the bottom: enhance NEO detection, tracking, and characterization capabilities. And this is what the NEOCAM mission is all about. The idea is to actually develop a dedicated facility for the use of finding, tracking, and characterizing NEOs. It's highly complementary to all the other facilities that we have, and it should provide us with a wealth of information about the population, as well as targets for future exploration. So from my perspective, there are just really a couple of critical questions that we really badly want to know about NEOs. We'd like to know when impacts will occur on human timescales as opposed to astronomical or geological timescales. And we'd like to know how bad they will be if they do occur. This kind of breaks down to finding the objects and getting good, reliable orbits for them. Of course, the how bad part really comes from the kinetic energy, which of course scales as 1/2 mass times the velocity squared. So of course we get the velocity from the orbit, but the key thing, the key parameter of all for the mass and the impact energy really is the size. That's important. Density is also an important parameter, but it scales linearly as opposed to the third power. So we'd really like to say something about sizes, and we'd like to get some information on density. And then of course we also want to get information on spin state, rotation, properties, shapes, multiplicity, porosity, all these other ancillary products, but we can't get those until we find the objects and have something basic that we can say about which ones are important for further follow-up. So why do we look for the asteroids in the infrared? Well, it's kind of for the same reason as a colleague of mine likes to say why criminals rob banks. It's because this is where the money is. In the case of the asteroids, they just simply are whopping bright in the infrared. Most of the energy comes out at thermal wavelengths. They get warm and they re-radiate brightly at these longer infrared wavelengths in particular. And of course, we've also heard throughout the meeting so far that the cumulative probability of an impact does depend pretty critically on the size frequency distribution. So not the H magnitude distribution, but actually the size. How many objects at what size is critically important for how often they could potentially impact the Earth. There is some evidence for a possible break in the H magnitude distribution at about 22nd magnitude, but this is about at the limits of our knowledge. We don't actually know from the NEOWISE data, which you saw some of yesterday. We can characterize the size and albedo distributions down to, a couple few hundred meters, but below that we really can't say. So it's possible that there's a change in the albedo distribution, and that's the result for the reason for the possible fluctuation in the H-mag distribution, but we just don't know. We'd really like to get better statistics on the population as a function of size and also as a function of albedo and how all of this correlates with orbital element space. So that is why we are interested in size, but of course, as I mentioned, it really comes down to the impact energy for the individual objects. So large uncertainties in diameter obviously translate into very large uncertainties in the impact energy because of that diameter cubed property. And with infrared radiometry, we can usually determine the diameter, not for every object, of course, but we can usually get the diameters to within 10 to 25% or so if we have good data, good SNR, the right wavelengths, and a reasonable sampling of the full rotational light curve. So it's powerful for that way, for characterizing large numbers of objects relatively quickly. And of course, it's very complementary to all these other techniques. You just heard about LSST. The combination of an infrared survey with visible light produces some really wonderful things. In addition to refining the orbits and so forth, you can also now get the albedo, which does correlate rather loosely, albeit with the taxonomy, and in turn with the density. So this again is starting to fill in some of these key parameters in the impact energy. So the question is, can we do this for individual objects of concern, but also for populations so that we can say something about the cumulative probability as a whole over the next century or so? So specifically, we tried to take the lessons that we've learned from working with the ground-based surveys and also with NEOWISE to try to design a facility that really is specifically optimized for this problem. So the idea is to really design a planetary defense mission optimized for detecting, tracking, and characterizing small bodies throughout the inner solar system, not just the near-Earth objects, but their source populations as well. And this is really critical decision support for stakeholders who actually have to make decisions about what to do next, about potential mitigation strategies. What you do depends on how much time you have and what you know about the objects at the time. So our goal is to really maximize the information that we provide. And of course, like I said, this is its sole purpose. We don't have any other science objectives. The sole objective really is to try to inform everybody who cares about the population of potentially hazardous objects, both as individuals and as a whole population. We project that with a reasonable telescope design, we could discover a few 100,000 new NEOs and millions of main belt asteroids, and that would be a significant improvement, even as we know them today. So this is what we came up with. It's a dual channel imager. It superficially looks a little similar to some observatories you've seen before, Spitzer and WISE, even Kepler. But the basic idea is to have a tall sunshade over here that keeps the sun on one side, because this is a heat-sensitive telescope. We really need to protect the thermally sensitive parts of the observatory by shielding them from the sun. But basically, the aperture size is really quite modest. It's about 50 centimeters, so it's just a little bit larger than WISE, which is 40 centimeters. But the difference is it's equipped with two 16-megapixel focal planes that now operate between 4 and 5 microns and about 6 and 10 microns. And the idea is to image them simultaneously with a beam splitter. But the key differences here are it no longer orbits the Earth. Unlike WISE, we would park it at the Sun-Earth L1 Lagrange point. And instead of relying on detectors now that have to be cooled down to about 8 Kelvin, which requires cryogen or a very expensive cryocooler, we would basically be able to operate these detectors at 40 Kelvin. And these are temperatures that at L1 we can achieve just purely passively with the right combination of shielding and radiators. So the back surface of the observatory here is painted a very special black. It's a ball infrared black paint, which is a very efficient radiator of heat. So I first proposed this with my team in 2005. This particular project has a long history. And we've been working diligently on the detector technology, but that really was spurred by funding in 2011 from the Discovery Program to mature the detectors. And we were awarded extended Phase A funding in 2016. So at this point, we've passed a series of reviews, and we've just passed our pre-key decision point B review. And we're waiting for direction from NASA to proceed to Phase B with the actual KDPB review itself. So I'll just say here a little bit more about just the design choices. We looked at lots of different options, and we've looked at many different design trades over the years. We've looked at visible, we've looked at infrared, large apertures, small apertures, co-hosted payloads, all these things. But at the end of the day, the configuration that seems to be the best balance between technological complexity and cost and capability is right around here. While it would be nice to have a larger aperture operating at these wavelengths, it just gets to be large and unmaneuverable, and it gets very expensive. But at 50 centimeters, we can cover a large solid angle on the sky and still efficiently maneuver from field to field. So we think this is right. In terms of capability, this jives pretty nicely with what Lynn showed. An observatory that is actually functioning with a ground-based observatory operating at about LSST's sensitivity here. This is from the NASA NEO Science Definition Team report in 2017, has the best chance of actually reaching that 90% mark on 140-meter objects, not actually H of 22. As Joe pointed out yesterday, when you take into account the low albedo portion of the NEO population, you really need to be shooting for completeness at about H of 23 if you really want to reach 90% at 140 meters, as opposed to H of 22. So again, searching with the two wavelengths where the NEOs are intrinsically very bright, right here, most of the light is coming out in IR. These are 3 different albedos ranging from low, medium, high, but also at the wavelengths where the stars of the same background depth are starting to fall off. The sky in these wavelengths is really quite blank, actually, except for asteroids. So it works really well. And we'd like to have longer wavelengths, but again, NeoCam's a bit of a compromise. We're searching in wavelengths where it's, this asteroid is bright, but we don't need to cool the telescope so aggressively that it becomes really difficult. And my colleague here is going to say a little bit in a minute about the cadence, but basically, we're going to cover a lot of sky. If there is something that's interesting, we can stop the survey and take a closer look. But just in summing up, we've been working on the detectors for a while. I think we've got them. Here's some papers that describe the process. They're in the 2048 format now. But just in conclusion, we've made a lot of progress over the last 20, 30 years in this field. And that's great, but we still have a lot more to do. And that's why we do surveys, because they do help us fill in the big picture. So thank you.
Thanks, Amy. Do we have any questions? I think they're speechless. That's good.
All right.
What is the wavelength range you intend to measure?
Sure. So there will be two channels. The first channel is a 4 to 5.5-ish micron channel, and the second is a 6 to 10 micron channel. And that's because that really samples the black body curve, and it lets us calculate a color temperature for the objects. With the cadence, Tommy will tell you about this in great detail in a minute, but the idea is really to use those two wavelengths with a cadence that's very optimized for NEOs, and we don't really have any other objectives. Go ahead.
Hi. Yeah, I just, not a question, just like to offer my congratulations to Amy and the whole team of NeoCam. The development of the detectors has been really impressive. I've been following this since 2003 or whatever, and that was a big bugaboo, and you guys solved it. Congratulations.
Thank you. Well, detectors are always the heart of every observatory, so it's been a partnership with JPL and Teledyne, and of course our good colleagues at the University of Rochester.
Great. So thank you. Let's thank our speaker again.